Hey there, ladies and gentlemen, boys and girls. Today we are going to talk about the evidence that supports the Big Bang Theory. All right, so make sure you guys have your handy dandy notebooks out. All right, so remember, a scientific theory is an explanation. It's an explanation of how something happens, and it's supported by evidence. How strong a theory is dependent on how strong the evidence is to support it. And there's lots of evidence that supports the Big Bang Theory. But we're going to highlight two biggest pieces of evidence, the two strongest pieces of evidence that support this idea of how the universe began. One is called Hubble's Law, also known as redshift. All right. And the other one is something fancy or a long one called cosmic microwave background radiation, or CMBR. That just sounds like it's something from space science. All right. So today we're going to talk about those pieces of evidence as we go forward. All right. Again, recap, Big Bang Theory is the idea that the universe started over about 13 billion years ago. All matter and energy were in a tiny, immensely dense, infinitely dense spot of matter and energy, and then outward, everything came. Not everything came outward as whole planets and things like that, but it went outward at pretty much the speed of light, and it's been going outward for the last 13 billion years, spreading out. Right? That is the current theory of how the universe began, or that is the strongest supported theory, I should say. All right. How we know about that is not because we can look back in time, or we can do, someone was there. All right. What we have to do is we have to look at what we see now happening today, and then take what we know, what's happening right now, and imagine if it went backwards, right? So we know time goes forward, right? And if the universe is expanding right now, if we go backwards, that means if everything's expanding, then everything had to have come back from a single place. And that's what we're going to talk about. The evidence supports that today. All right. So we're going to talk about the two different things here today. And the first one we're going to talk about is Hubble's law, or what we call redshift. And it relies on a big idea that we've already talked about. That's called Doppler effect. If you don't remember what Doppler effect is, flip back through your notebook and look at Doppler effect. We talked about it in terms of sound waves, right? We talked about it in terms of a car. So if I have a car that's going, here's my fancy car, going, right? As it's coming, it's producing sound waves. And me as the observer, right? As it's coming towards me, the sound waves in front of it are kind of bunching up together, right? They're closer together because it's kind of catching up to its own waves. That's giving it the appearance of a higher pitch for me. And the moment it passes it on this side, it's still giving off sound waves, but the sound waves are moving in the opposite direction. It's moving in the opposite direction. Sound waves lengthening its sound waves, and thus making it a lower pitch. So it gets that, all right? Light waves do the same thing, all right? Remember, the only reason why we ever see anything is because light waves comes in. But there are a lot of light waves we don't see. We only can see visible light, right? But we have technology that can help us see light waves that don't come from that. So let's say, for example, here, so let's talk a little bit about what redshift is, and then we'll talk about how that applies to what we call Hubble's law. All right, when we look out at the universe, all right, when we look at, let's say, stars, stars of different galaxies, or from far away from us, right? So I got a star here, or even just looking at other galaxies. Maybe another spiral galaxy like ours, all right? If they are in motion, right, we would expect that one side of their waves would be shorter and the other side would be longer, right? And so what happens is, right, on one side of those waves, the wavelength, so let's say the star is moving in this direction here, the wavelength would get a little bit closer together, right? And on its opposite side, the waves would be getting longer, wavelengths. right? Now, with sound, this one it meant a higher pitch and a lower pitch, right? But with light waves, we perceive them as parts of the electromagnetic spectrum, things like ultraviolet and infrared, the color blue and the color red. All right, and so what we know here is that when an object is moving, say in this direction, there are going to be light waves that are in front of it that will come off as the color blue because it's got the shorter wavelength, and behind it, it's going to come off as the color red because it has those longer wavelengths, just like when we talked about the Doppler effect. But now here's the thing, right? And we can see that from our beautiful home on the planet Earth. Now remember, we talked about we have special telescopes on our planet, right? We call them spectroscopes, and they gave all the peaks and the colors and the lines and stuff like that. We have these special telescopes on our planet called spectroscopes. Right? And what they do is they're going to pick up those wavelengths. And we notice that when we look at a lot of stars, we pick up a red wavelength. When we look at a star. Now, that doesn't necessarily mean that star is the color red, right? Because these spectroscopes pick up not just visible light, they pick up colors of things that we don't see with our eye. So when we look at the waves of the wave, or the types of waves that we can't see with our eye, we notice that they're red. But not just that stars are doing that, even galaxies, right? So if this galaxy is going to be in motion, we notice that when we look at this galaxy, the wavelength that kind of approaches us is a very long wavelength in the color of red. It's almost like the wavelengths coming off of it had shifted into the color red. And the other side here is what we call blue shift, where it's shifted in front of it in the color blue. Right? So that means that this galaxy is also not just moving away from us, but they're starting to go in opposite directions as well. They're spreading apart from each other. And we notice that every object with our spectroscopes, every object we see in the sky through our spectroscopes are not only just moving away from us, they're moving away from each other. Almost like it's spreading out or expanding. Right? And we notice this as we pick this up. A lot of these light waves, a man by the name of John Hubble started graphing a lot of this stuff. And we can measure how fast away this galaxy is moving and how far away the star is moving, but basically how red are these? Are these wavelengths just spread out a little bit, or are they really spread out? That tells us how fast they're going. Other bell. All right? And so what John Hubble did, noticing this redshift, is he plotted his points on a graph. And where he said, okay, here's the speed of the stars, which he measured using the red, how much red there was in that red or in those wavelengths, and then judged that based on their distance. Right? And what he got is he got a bunch of data points. He got a bunch of data points as he measured all these different stars in the galaxy. He got all these data points that kind of all looked like this, his data. And it all came into a trend. Where he said that, okay, Hubble's law states that all stars and galaxies are spreading out from one another. And the further away it is, the faster away it is. So the ones that are the furthest stars away from us are moving away from us even faster. They're expanding way out there, all right, and going really, really fast, even at the border speed of light, all right, away from each other. The ones that are a little bit closer to us are moving away from each other, but just not quite as fast, all right? You think about it, as things are starting expanding, the more space you have, the easier it is to kind of keep moving there, all right? So that's what we call Hubble's law. Again, recap Hubble's law. When we look at moving objects, they give off light waves. Because they're moving, some light waves shrink, or wavelengths shrink, some wavelengths extend, just like Doppler. It's the Doppler effect, right? But with light waves, this comes off as the color blue because blue has a short wavelength. This comes off as the color red because red has a longer wavelength. We call that red shift. Right? We notice that all the objects in space have a red shift on them. Right? Now when I say all these objects, I say all large objects here. We're talking about stars, and there are asteroids and things like that, smaller objects that can be flying around in different directions and stuff like that. But when we look at the large objects, kind of the universe as a whole, we see this red shift, right? And then the fact that the farther away it is, the faster it's moving, we call that Hubble's law. All right? Okay, so we're halfway done. I know this is going to be a long one here, but there's a lot of evidence here. All right, this next one's called cosmic microwave background radiation. All right, long story short, all right, because then I'm going to explain it a little bit here. Long story short, it says the universe is currently cooling down. All right, universe is starting to cool down. So to kind of talk a little bit about that, I have a little demonstration here using a balloon. All right, so if we think, all right, the idea at this point is that, especially after we did Hubble's law, we talked about Hubble's law, the universe is growing bigger, right? That it's expanding, right? So not only is the stuff in the universe expanding, but the energy should also be expanding, and we know that energy travels on waves. All right, especially through space, we would talk about electromagnetic waves, radio waves, microwaves, infrared, visible light, all right, ultraviolet, X-rays, and gamma rays. I should finish them all. All right, so what I have here is a little balloon. All right, now what I did on this balloon, all right, it's a little tough to see. Well, let me fix a little bit here. Here, all right, I drew a wave. All right, it's a little tough to see. Being a little bit difficult here. There we go. All right. Now I can measure that wavelength. All right. I can measure that wavelength right now. I could say how close each one of those crests and the crests are. I'm measuring it at 1 centimeter. All right. 1 centimeter. That's a pretty short wavelength. All right. If I was going to say this is a short wavelength, if I'm going to talk about electromagnetic waves, I'm going to say maybe this is like X-rays or gamma rays. And also look how close the stars are to each other. But as the universe expands, these waves are going to start to spread apart. So do the stars. They're starting to spread apart from each other. So if now we have a little bit longer wavelength, here we go. Let me see. I was at 1 centimeter. I am now at 3.5 centimeters. If this is an electromagnetic wave, I went from a very short one to a little bit longer. Maybe let's say ultraviolet right here. Spreading them out. Visible light. Infrared. All right, now, not only are all the stars spread out more and more, but this wavelength has dramatically increased. I started at 1 centimeter, and now I'm at 6 centimeters. All right, I started at, say, gamma rays, X-rays. I moved along to the point where we find this. We find microwaves in our universe. All right. All right. What we do is we've taken, by accident, we discovered this. By accident. We were trying to figure out some other stuff, and what they did is they pointed a satellite, basically a telescope, out into the dead space, or into dead space, basically just a black square of space. They were trying to calibrate it, this type of microscope, and they kept getting this interference. They kept picking up these waves. Like, I'm just pointing it at nothing. I'm trying to just calibrate this the telescope. I'm just pointing at nothing. What they realized is what they were picking up was microwaves. And then they said, well, okay, maybe it's that spot right there. Let me point up this blanket spot right here. Microwaves. Microwaves. Not the machine, the wavelength called microwaves. They're not just finding giant machines. All right? Microwaves, microwaves, microwaves. And what we realize that everywhere around us in the universe is microwaves. Now remember, microwaves, electromagnetic waves, they have waves, but they are, right? Microwaves Microwaves have a very long wavelength. Right? Because they have a very long wavelength, they have low energy. In this case, that would mean that the temperature of the universe, low energy means low temperature. Talked about temperature. All right. But if it's stretched out to the point of where we have microwaves now, if we went back in time, right? We went backwards in time and we just took that wave, but it was just a little bit shorter, a little shorter. All right, to the point where we get something that's very high energy. This is the past. All right, this is very high energy. Look at those wavelengths. That wavelength means higher frequency. Higher frequency means higher energy, which means the universe was once very hot. Again, all right, it's just that we find this background radiation, literally energy in the background in space in the form of microwaves. All right, this is what we find today. But if we turn back the clock, that those waves must have, and if the universe is this big now, just like my balloon, all right, if we turn back the clock, right? So all the evidence we have now is based on, okay, here's what we see now. What if we see what we're seeing now, that that objects are going apart from each other? We turn back the clock, that means they all had to be in the same space. You may notice that right now, the universe is, all the energy is very spread out. Those wavelengths are very stretched out, just like my balloon. I stretched it out. Well, if it's expanding and stretching out now, if I turn back the clock, all that energy had to have in the past been into a single point. To the conclusion that we have in the Big Bang Theory is that the universe started where all the matter and energy in the universe started back in a single point. And all the matter and energy in the universe today is now expanding for the last 13.7 billion years. Okay, so that's our two pieces of evidence there about Hubble's law and then about cosmic microwave background radiation. I know this is a long video here, but got to talk a little bit about some of the stuff we've already talked about, spectroscopes and light waves and wavelengths and stuff like that to kind of put this all together. All right, so hopefully I have you guys in this in your guys' handy dandy notebooks. If not, go back and fill that in, and then ask me any questions if you have any. All right. Otherwise, I'm going to cut this off now before I hit the 18-minute mark. Thanks for watching. Good luck, and may the science be with you.